exponentials and multiply them. And by product of finitely many exponentials, you can get an arbitrary group element, assuming it's connected. And the proof here uses path connectedness, and basically, I think probably, it's got to be group multiplication, right? And some compactness arguments and so forth, and then he gets his corollary. If G is a connected matrix Lie group A and H is a matrix Lie group, and you have Lie group homomorphisms from G into H, if you have associated Lie algebra homomorphisms, if the Lie algebra homomorphisms are equal, then the Lie group homomorphisms are equal. So, in other words, if you have if you have two connected Lie groups, all right, and they have let's see here how to say this. What? Oh. He's comparing the group homomorphisms and the Lie algebra homomorphisms. I'm sorry, I wanted to say something else. Alright, it's just a quirky result, whatever. Anyway, from that he gets that every Lie group is a smoothly embedded submanifold of n by n complex matrices. And he also gets this result: every continuous homomorphism between two matrix Lie groups is smooth. That's pretty nice. You have continuity, you get smoothness. That's a pretty good deal. I trade you no derivatives, you give me infinitely many. Yeah, that's not too bad. And you notice what he has next here is that corollary 2.35, your matrix Lie group with the algebra G, then the matrix X is in G if and only if there exists a smooth curve gamma such that gamma of T lies in G for all T, gamma 0 is the identity, d gamma dt is equal to X, thus G is the tangent space at the identity to G. Yay, we finally got the thing I've been using. It's been justified. Corollary 2.35 has now established that, in fact, I was justified in saying that frac G was identified with the tangent space, the identity of the group. That brings us to the study of Lie algebras, which is what I wanted to start writing in. I mean, I hope you guys read this section. I mean, this section that's heavy lifting, that section. And, I'm just trying to get you guys started on this topic. I'm not trying to prove everything in here. I'm going to try to give you an honest, at least partial proof, if nothing else, of the Baker-Campbell-Hausdorff. Now, I have been discouraged from doing that from people who know more than I do, or fresh on more than I do, which is that why would you prove that? What's wrong with you? Why would you try to do that? And they're probably right, and I'm probably going to regret it. I know it's the core of everything that's going on. So like a moth drawn to a flame, it's much like linear algebra. I probably shouldn't prove the Jordan form, but I know it's central to everything, so until I personally own it, I can't stop teaching it. Once I completely own it, then I'll stop teaching it, and then people will be happier with my teaching. But oh well. All right. Okay. This is a really fun direct calculation, by the way, guys. I recommend that. It's not that hard. You can do it in a half hour. It's not that bad. I think I used induction. I don't remember.
Used induction?
I think maybe. I gotta find that. I'm not sure that way. I gotta find that. You know what else? I need a projector in here, don't I?
Projector?
Yeah, if I had a projector in here, wouldn't that be nice?
I don't know. Projector never usually goes well for me.
Oh.
It allows you to go too fast. That's what it usually happens.
Me too fast? Never.
Yeah. When you have to write things, then at least I can take that time.
Yeah. Fine. By the way, you should make sure you understand corollary 2.32, the one I got tired of understanding. The proof of it's very fun. The proof is totally understandable. I don't know, that's a fun one. That's a fun one. Okay, what is a Lie algebra? Let's talk about that for the time that remains. We've got some time. When do you guys have to go?
I mean, this 5:15.
5:15? Okay.
5-ish, 15-ish.
5:15-ish is okay? All right.
5-ish, fine.
All right. You never know when we're going to have another birthday party pop up. Let's see here. Lie Algebras.
Trampoline and bowling.
You know, did I talk to you guys about Lie Algebras in another course I've had with you? I can't remember.
Definitely not me.
No? Okay, cool. Cool. You can talk about a finite dimensional real or complex Lie algebra. What is it? A Lie algebra, finite dimensional. I'll keep it a little bit over F, a field, all right. Is a vector space. Let's say and I'll just get straight to the letter frac G. That's our notation for Lie algebra. Over F, paired with a bilinear anti-symmetric bracket. Here's the notation like this. This is a mapping from the Cartesian product of G back to G again. Let me unwrap those words for you. I think you know what bilinear means, all right? You guys know what I mean by bilinear?
It's symmetric.
So like if I
Linear
do,
in both slots.
right, if I do slot like this and then I fix this, that's not very good. Anyways, it's linear in both slots, right?
Yeah.
Okay, so I'm just gonna leave it at that. We've talked about that before. I don't want to belabor that. I mean, fine. 2. This is the antisymmetric. XY is equal to minus x of yx. And then 3, and this is the thing I haven't said in words yet. It's a bilinear antisymmetric bracket satisfying the Jacobi identity. And then I'm enumerating that. That is linear in both slots. Bracket of xy is minus bracket of yx. And this. And so the way I remember this, guys, is just I go in cyclic order with x, y, z. So the way to understand this thing I'm writing right now, what is the Jacobi identity? How should you sort of internalize the concept of this? What is it measuring? What the Jacobi identity measures is the departure from associativity. It's basically saying, okay, it's not associative, but it's almost associative. So if I do one bracket and then another, if I do another bracket then another, I mean, which one comes first or which one comes second? I mean, it's not associative, right? I can't just say associativity would be if I could like equate any two of these, right?
Mm-hmm.
And finite dimensionality is, well, finite dimensionality of the goodness gracious. Right. Of the vector space, as a vector space, right? So there's different things you can do here. Now, typically, what we're doing right now, we're either going to go with a real one or a complex one. There's tons of things known about Lie algebras. There's basically, this is an abstract definition, right? But it has been proved that finite dimensional Lie algebras can be, they are isomorphic as Lie algebras to matrix Lie algebras. the proof of that is not entirely trivial, but it can be made. And there's something called Adu's theorem, in particular, that says that given a finite dimensional Lie algebra, you can find matrices sufficiently large so that the Lie algebra is simply the commutator bracket on n by n matrices. So an example of this, like the quintessential example, is frac G, right? Equal to like GLN over the field and the thing we already been doing, right? You can prove that the commutator bracket satisfies, I mean, it's clearly bilinear, right? It's clearly skew symmetric, and I think I gave you an exercise somewhere to show the Jacobi identity is true. Did you suffer through that, Bradley? I can't remember.
The what?
Have you ever shown that this satisfies the Jacobi identity?
I don't think so.
It's not hard. It's like,
It doesn't seem hard.
no, you can do it in like 2 minutes. It's not a big deal. But that's a fun matrix problem. All right, so in fact, when I write this little GL, I'm actually equipping, in my view, when I think about this is I think this is like, I don't think I told you guys this before, I think of this as the n by n matrices over F paired with the commutator bracket. I think of, when I talk about little GL, I'm thinking of a Lie algebra, right? What's a sub-Lie algebra? Let's say H is sub Lie algebra.
So that's a subspace with the same Lie bracket.
Yeah, it's a subspace in the sense of vector spaces of G, and H is a Lie algebra. With respect to what? The bracket on, the bracket restricted to the bracket of G restricted to the Cartesian product of H and H, right? You can talk about real subalgebras versus, think about complex Lie algebras, right? Complex subalgebras. What's a Lie algebra homomorphism? What's a Lie algebra isomorphism? What's a Lie algebra automorphism? Right. So, of course, if we have, and I think I mentioned this already, but I'll mention it again. So if I have psi of xy, right, is equal to psi of x, psi of y, right, and psi is a mapping from Lie algebra G1 to Lie algebra G2. So here we have the bracket of 1, over here I have the bracket of 2. That makes psi a Lie algebra homomorphism, right? And then, if psi is a bijection, it's a Lie algebra isomorphism. If G1 is equal to G2, and it's an isomorphism, then it's a Lie algebra automorphism, as I was mentioning to you. This is a subalgebra of a Lie algebra is again a Lie algebra. Oh, he's defined it in a slightly different way, but by definition is equivalent, given his sentence. He says a real subalgebra of a complex Lie algebra is a real Lie algebra. You could look at a subspace which is closed. Like every complex vector space can be viewed as a 2n dimensional real vector space, right? So if you have a subspace of a complex vector space, which is a real subspace, right, and then that is closed under brackets, that would give you a real Lie subalgebra of a complex Lie algebra. You could think about that, and we do. Oh, and here's the theorem of Adu. Theorem 2.40. Every finite dimensional real Lie algebra is isomorphic to a subalgebra of GLNR. Every finite dimensional complex Lie algebra is isomorphic to a complex subalgebra of GLNC. So there's that. he defines, now look at this. This is a new add, right? Notice how adjoint is defined now, little adjoint, for Lie algebra, for GLE algebra, right? I haven't said boo about a Lie group, right? I mean, there's no Lie group in here. This is all just formal abstract algebra. And so you can define a linear map how? Define add sub x, a mapping from frac G to frac G, by fixing, you just basically, so what it is add x of y is equal to xy.
It's 5 o'clock p.m.
You have a good reason to make this definition because we just saw that under the commutator bracket, when we look at the specific context of matrix Lie groups, out popped this relation for the adjoint mapping where we had understood it as being the derivative of the conjugation map. Right? We look at the conjugation map to start with because it has cool properties and other things I forget. To basically differentiate that, you come to the little adjoint, and then we worked out that the little adjoint basically acts as the commutator on matrices. So it makes sense in the abstract context to define this abstract little adjoint, and that will give you a linear transformation from frac G to frac G, right? In other words, we have that the adjoint of x is an element of GL frac G, right? It's a representation of the algebra onto itself. No, he says, well, that's kind of stupid. Like, why would you do that? Isn't that just another notation for the commutator anyway? But,
More broad than the commutator.
well,
Anything that.
basically his point is just, I mean, his point is rather pragmatic. He's like, do you want to write this? Or do you want to write
X.
That's it.
what do you want to write? And then that series, that purple I erased, right? It was another, in the notation of adjoint, it was actually really simple. Right? And then like e to the adjoint even makes sense as like the exponential of an operator. Okay, so his next proposition says that the adjoint is a Lie algebra homomorphism. Claim. Add x. So, okay. Cool. Let's see here. So we start with, we want to look at the adjoint of x acting on, say, yz. What I want to show is that that is the bracket, right?
X, Y, X, Z.
Exactly. So this is by definition x, y, z. Now I can trade that by the Jacobi identity for what?
Y,
Minus
X, Z, Z, X, Y, or plus Z.
Right, so what I'm going to do,
Minus Y.
Yeah.
let me be just slightly lazy. What I'm going to do is I'm going to look over here at this, right? And then I'm going to say it's equal to these two flipped. Because to flip them is to put a minus, put them on the other side, and that way I've got a valid equality. So this would be, now this may not be the absolute most efficient way, but we might still need to make another step past this in order to see what we got. Oh, how about, I'm not going to flip that one. I'm going to leave it minus. I do want a minus in here, after all. Thinking ahead a bit. Duh. Let's see here, what do we got? We've got, this is the bracket, that is, well, what am I trying to do? That's the adjoint of z acting on x, right? And this would be what? This would be z, and this is the adjoint of x acting on y. I'm not sure I'm going in the right direction. We'll decide in a second here. I should probably write down what my target is so that I'm not working in the dark here. What's my target?
It's a bracket of adjoint x, y, adjoint x, z. So maybe instead of saying adjoint zx, you should flip that and say.
Right. I definitely want add x's, so that's a bad choice, right? I should instead write that minus. It's adjoint xz, right? I have somehow confused myself here. I thought that's what I want. I want. So, bracket, right? Got an add x of, well, I mean, I can't, the thing is I can't assume it's a commutator, right? I don't know that this is a commutator bracket.
Oh.
I can't just write it as multiplication.
Ah,
That's
yeah.
not allowed. This is an abstractly bracket. I know.
So
yeah.
what? I mean, you can't do much with it then.
I am stuck with the axioms. I can use bilinearity, I can use antisymmetry, I can use Jacobi. That should be enough.
Yeah, can you I think you know that like maybe you can like add 0 because like wouldn't I'm not sure that helps.
This shouldn't, I don't know what I'm doing here. I have managed to make this, I don't know how I got lost in this. This one I don't remember being difficult. Like, I have worked this out before. Oh. Oh, I'm an idiot. It is the commutator bracket.
What it is?
No. Wait a minute, no.
So do the opposite.
Oh, that's not what we want to show. This isn't what we want to show. What we want to show... Okay, so,
Trying to show that you can do step 2.
I want to show that... No, sorry, I'm still... It just slipped my mind. I had it, and lost it.
Oh, it's add bracket xy.
Yes. Add x bracket, add y, acting on c. Does that make sense? He made it starting with the same. Well, he's got. Oh, I'm a dummy. Oh, I'm trying to. No, I don't think this is true. I think what I'm trying to prove right now is not true. Like, that's as far as you go. You're stuck. That's not what he tries to prove. What he tries to prove, not like this, that add of x, y. Okay, that's the bracket.
Mm-hmm. Yeah. It's going to be the
Acting
bracket
on
of
Z.
add x.
And I think I
add
should
y.
say add.
Yeah.
No, I should.
No,
I'm
add
sorry.
x.
Yeah, this is supposed to be what we were saying. Add x, add y. Is that right? I'm not sure.
I'm not sure if that's true.
I'm having
Yeah.
having issues.
And they're both acting on Z.
Yeah. Now to make sense of this, we have to let this act on z. Now that
But if we're keeping the x.
this here. See, the thing is, this is actually the commutator bracket because that's happening. This is where is this going on? This is going on in GLG, which for all intents and purposes is k by k matrices where k is the dimension of the Lie algebra. That is, honest to goodness, the commutator bracket, which in this case is the composition of operators and then subtraction in opposite order, right? That's still true here, even if it's more abstract conduct.
But if it's mapping frac T to frac G, wouldn't it be the same?
Maybe that's an error.
Or maybe it's
What I'm
maybe it's
supposed-
just add from G
Yes.
to GL. Oh,
Right, that's more
That makes
interesting.
so
So we
much
have
more sense, yeah.
yes. So it's mostly user error, mostly me. Sorry. Should let you guys write. Next semester, I'm gonna let you guys write. Make my life easier. Oh, my throat's gonna kill me when I go home. Yeah. So now that there's hope for, right? Because then you just let this act on Z, right? I mean, if we started with that side, it'd be even easier, I guess, but... Which I guess is what? This is bracket of xy, bracket z. Which is equal to what?
The Jacobi identity thing.
Yeah, the Jacobi identity thing, which would... What are we going to do here? This one... I guess I want this one. But it's in the... I mean, put that on the other side, so it would be x... yz plus yzx. And that, right, would be, this would be add x of that bracket. Maybe I shouldn't be writing yet. Let me stop and think before I just go. I mean, I can write, but who cares? What are we trying to do? We're trying to get it to add x of add y.
Yeah. No, I think you're good. X
Oh.
should be a minus. It'd be 1 minus.
Should be.
Now let's see here, add
I think-
y. And the minus I can get from switching these in bilinearity,
Yes.
which I need to do.
Right, yeah.
Otherwise I got the x in the wrong slot, right?
Right.
That's where the minus comes from. Okay.
And now we're looking at add x of add y of z minus add y of add x of z. You pull the z out and you've got add x, add y, bracket, acting on z. But this holds for arbitrary z, therefore it's an identity. Which shows, of course, that the adjoint is as claimed. It is indeed a Lie algebra homomorphism. When is it an isomorphism? You need the kernel of the map to be 0, right? So for the kernel of the adjoint mapping to be 0, we would need what?
Would need to be the identity map.
Yeah, it's like the only thing that has bracket with the whole Lie algebra being 0. 0 itself, I think, if I understand this right. Right. For this, in other words, if this is the 0 map, what's that mean? This being the 0 map would require that x bracket y is equal to 0 for all y.
And that's not the commutator. The x is Earth.
So x would have to be 0. Well, no.
Right, x equals 0 is in there. The question is more in there. Is there some subspace of the Lie algebra that, when bracketed with the rest of the Lie algebra, is 0? There could be. So there sometimes the adjoint would be faithful. I mean, would be an isomorphism. Sometimes it wouldn't. Anyway, that's all for today. Thanks, guys. I got more done than I thought we could get done. I'm kind of surprised. My general lack of stickiness.